lossy transmission lines is the next topic that we're going to talk about. Let me lead off with a little teaser question here. Let me tell you a little history. We talked at the beginning of class about the telegraph and how that was sort of one of the first uses of transmission line equations. It was such an important use that those original transmission line equations that we derived the solutions to that system of equations was called the telegrapher's equations. And it turned out that this enabled high-speed, long-distance communications. The first ones were kind of deployed along the East Coast in the U.S. And then they got ambitious. And I believe it was about the 1860s, circa the Civil War era, that we decided, let's try to do this across the Atlantic Ocean so that we could send messages to England and Europe, back and forth. The idea is very simple, right? You just take a transmission line, jacket it, make sure it's waterproof. You can put some regenerative repeating in there even using some relays. Relays are very robust. It's electromechanical switches. That means you have to send some DC current down the line too. But you basically, you lay a long cable that connects the two continents under the ocean, and in theory that should enable communications. And that's exactly what happened. They laid it. I believe the first one didn't work. It broke or something the first time that they laid it. So they tried it again, and they actually were able to make an electrical connection between the two continents. And that was like in the 1860s. Now, let me do a little survey. How long was it, do you believe, until they had analog voice channels for an undersea cable or undersea communication network? How much longer did it take? Because remember, the phone wasn't invented, the telephone wasn't invented that much longer after that. I think that was 1860s or 1870s. Alexander Graham Bell, they were building the first telephones. How much longer after that did the first undersea transatlantic voice cable get installed? How many people say the 1870s? Raise your hand. You think engineering was fast enough to do that? Yeah, so there should have been like a Moore's Law for telecommunications back then or something. Surely should have worked then. How about 1880s? We had one taker for 18. Yeah, that's a little more reasonable. You get 20 years of innovation. You could do that. How about the 1890s? Anybody raise their hand? 1890s? What about the 1900s? Between 1900 and 1910. Yeah, a lot more people raise their hand. That seems like 40 years of innovation should solve that problem. How about the 1920s? Anybody? 1920s. You don't have a lot of faith in your fellow engineers back at the turn of the century, do you? 1930s? Anyone? 1940s? 1950s? Nobody raises their hand for the 1950s. If you did, you would have won that question. Oh, yeah, now you do it. Now you do it. Nice. Yeah. I know. You had more faith than you should have. Well, it's actually not the faith in your fellow engineers. It's your faith in physics, right? It turns out there was not an easy way to transmit a signal across a very long distance that wasn't digital, actually. If you think about it, you can use relays to regenerate and boost the power of an electromechanical system like a telegraph. But if you have an analog voice signal, you've got to find a way to regenerate analog signals with frequency content in the tens of kilohertz. Above 1 kilohertz, basically. And then you've got two things working against you. First of all, it's an analog signal, and we didn't really have a good way to amplify analog signals back then. How would you have done it if you were in the early 1900s and you wanted to amplify an analog signal? What technology would you have used? Vacuum tubes. We hadn't invented those yet. That's what was invented in the 50s that allowed us to. You get the right answer, eventually. That's it. Those transistors weren't invented until the 1950s. It turns out before that we had to use vacuum tubes. And anybody who hears stories of their grandparents with vacuum tube technology in their radios or their television sets knows that what happened every couple of times you watched the device. you blew out a tube and you had to replace it. Vacuum tubes are notoriously unreliable. And it turns out that when they're miles beneath the ocean at the bottom of the Atlantic, you can't exactly replace them on a regular basis. So for that reason, any type of large-scale communications didn't really happen in the analog world, even for simple, what we would consider narrowband voice channels nowadays, until the 1950s, when we had a solid-state, rugged technology that we could put under the ocean, set it and forget it, and amplify our voice signals and talk to people in Europe. So that was one aspect, regenerative repeating. The other thing that we're going to learn today is that the transmission lines get exponentially lossier as you go up in frequency. So there is actually a big difference in loss when you go from a telegraph signal, which is in the tens of hertz, to a voice signal, which is in the kilohertz regime. That's several orders of magnitude of both frequency and, it turns out, also loss per unit length of cable. And that's what we'll talk about now. So let me lead off by drawing our familiar two bars. Probably one of the last times I'll ever draw the two bars in this class. It is kind of sad. And it would be disheartening if it wasn't for the fact that we're about to get into field theory. Hallelujah. So, we're going to go back to basics here. And once again, I'm going to blow up a tiny section of this transmission line and model what does a lossy circuit look like, a lossy transmission line segment look like. We're going to modify our model, per unit length model, in two ways that introduce loss. And depending on the actual physical implementation of your line, one way or the other is usually going to dominate. So where we had per unit length series inductance, we are now going to add per unit length series resistance. And let's see, we're going to have an R in units of ohms per meter. And whatever length here, delta Z, we are going to multiply delta Z times R to give our total resistance for this segment. Delta Z times L is our per unit length inductance. And now, where we had per unit length capacitance, we still have per unit length capacitance. But we will also have another loss term here called shunt conductance. G, units of Siemens, 1 over ohms, times delta Z. This is our new term. Everything else is the same, but our new terms here are series resistance. And this is per unit length. Units of ohms. Let me draw specifically what we are talking about, that R value, ohms per meter. And we call this shunt conductance. And of course, this is also per unit length. Units of Siemens per meter, mhos per meter. I think that's an older convention you may see in older books. Mhos. Like, oh, we just flipped ohms. Let's just call it a mho, M-H-O. So this is now our circuit model that we use. Before I get into actually what this means in terms of our voltage and our current equations, let's assign some physical attributes to what these loss terms mean. Because they tend to manifest themselves in different ways on different transmission lines. Series resistance is probably the easiest one to understand. If you think about the transmission line that we did for the power transmission, or if you're thinking about like long distance coaxial cables, you're sending current waveforms to and fro on metal. And unless that metal is made out of a superconductor with infinite conductivity, zero resistance, you're going to get some sort of I squared R losses, some series loss, which will cause the waves that are traveling on that device to expend energy as they move down the line. So as a result, there's always a little bit of this. And it tends to get important when you've got a transmission line that has miles and miles, or at least meters and meters of cable, depending on the frequency. For the power company, it's miles and miles of transmission line, and you'll start to see some significant I²R losses. When you're sending a telephone signal to your house, or cable, coaxial cable for your cable TV, then it's hundreds of meters of cable is leading to some losses of your signals. So that's just ohmic losses. That's relatively straightforward. What causes shunt conductance on a transmission line? There are a couple different mechanisms that we all model with a shunt resistor in place. It could be some leakage conductivity in your dielectric. If your dielectric material is not a perfect insulator, if it allows for a slight amount of conduction current to and fro, then there could be hopefully a very large or a very large resistance value, a very low conductance value for that shunt conductance. Hopefully it would be such that you could ignore it completely. There are some instances where you have maybe imperfect dielectrics where you actually do get some shunt ohmic losses. Another form that can be modeled like this as a shunt resistor or conductance in the circuit are some dielectric relaxation losses, which occur at very high frequencies. You don't usually worry about that when you're doing 60 hertz power, but if you're doing microwave engineering, that can be an issue. Dielectrics can become lossy because there's literally a time lag between the excitation and deformation of electrons around a molecule, and they're springing back when the field is reversed in an oscillating field. And so as a result, it becomes kind of like pushing the child on the swing at out of phase, right? You get a ticked off child that absorbs a lot of energy instead of swinging higher if you don't hit them on the right phase. So that is a mode of loss. Okay. So now, it turns out that if you went through all the math like we did the first day of class, remember how we set up our Kirchhoff voltage and current loops, and we took the limit of delta z going to an infinitesimal amount. We got a differential equation, partial differential equation, and we said the telegrapher equations solve this different partial differential equation. Let me just cut to the chase and save all the derivations. So to quote an old Far Side cartoon, it turns out that the voltage and the current phasor solution looks remarkably similar to the thing that we're already used to studying. It only differs in a couple minor regards that make a big difference in terms of signal transmission. But mathematically, it looks almost the same. My voltage as a function of space, of course it's a phasor, so I'm going to put a squiggle on it. It's a function of position z, is going to be equal to some complex amplitude and phase, which is the amplitude of my forward propagating wave, exp to the minus gamma z. I'll show you how to compute gamma in a second, but gamma is our propagation constant. Notice there's not a j there yet. I'll show you where the j comes into play. Plus v minus exp plus gamma z. And if you haven't guessed already, the current solution phasor is going to be the exact same thing. We're going to define the same value in intrinsic impedance, that's a constant. And we're going to have the exact same phase terms up here. Put a minus sign there, backwards traveling wave divided by the impedance, exp to the plus gamma z. And now our constants are something different. Remember, where Z0 was originally the square root of L over C, the per unit length inductance over capacitance, it's now a more complicated expression. It is the square root of R plus J 2 pi, the frequency that you're operating with. I like frequency. Some people call omega 2 pi f. They'll use omega instead of 2 pi f. Tomato, whatever. Times L, per unit length inductance, over conductance, shunt conductance, plus J omega C, per unit length capacitance. Now let me be consistent. J 2 pi f C. So this is units of ohms, units of ohms, units of 1 over ohms. This is also units of 1 over ohms if you work it out. So I have basically square root of ohms squared, which is ohms. So I've got something that's an impedance. But remember, and this is probably one of the more peculiar aspects of transmission lines. Remember how I said at the beginning of class, when you have a purely real Z0, intrinsic impedance, that does not represent ohmic losses. It is the ratio of voltage to current that the device naturally carries. And because it was real, what that meant is that voltage and current were in phase. Back when we were doing non-lossy lines. Now, we have a complex Z0. And it is one of the ironies of life that a complex Z0 actually indicates a lossy line. The presence of a J something in the impedance indicates loss. It implies that voltage and current are being carried out of phase with respect to one another, which can only happen actually on a lossy line, not a linear lossless line. And I say that's ironic because if you think about it, like if you're talking about a load that you learn in circuit class, when it was purely real, it was a purely resistive component and it was absorbing power, and it had an imaginary part. That imaginary part was like an inductor or a capacitor that was only storing power. And so there wasn't any lost power. But here it's kind of the opposite, right? Z0 real, pure lossless line. Z0 is complex. That's the sign that this is a lossy line. And indirectly implies that it is a lossy line. Predominantly it implies that voltage and current are not carried with the exact same phase as they are on a lossless line. That's one constant. There's another constant here, gamma, my propagation constant, which has the following form. We write this as alpha plus j beta equals to the square root of r plus j omega, 2 pi, be consistent, 2 pi fl, where f is in hertz, times g plus j 2 pi f per unit length capacitance. So you see that the propagation constant for a lossy line is complex. It's got a real part, which we call alpha, and that's our attenuation coefficient. And the beta is the same old beta that we're used to. This is the wave number. Units of radians per meter. And technically this is the same units, but in attenuation we call it Neppers per meter when you're not doing angular things. And so you can see that this more complicated form collapses to the form that we're used to whenever G and R are equal to 0. When the shunt conductance and the series resistance vanish, we're back to our normal expressions. These go away, J2 pi f's cancel, and we got square root of L over C as our impedance. When R and G are 0 here, we collapse this down, and we get basically J2 pi square root of LC, which winds up being our propagation wave number that we solved for in our original expression. Everything behaves as normal. The only difference is that this alpha can be non-zero when R and G start to show up in the network. And what that means, it will be a positive value that comes out of this. You can show that. And for my plus Z traveling wave component, when alpha is positive, that actually means that there will be exponential attenuation in the positive Z direction, a decreasing wave. For the backwards propagating waveform, that will mean that as the wave travels in the minus Z direction, you'll have that same plus alpha constant. And again, there will be exponential attenuation in the minus Z direction. So it doesn't matter which way you go on this line, you're going to lose energy. You're losing power in your waveform. Can anybody think of a transmission line that has a negative alpha? It's actually not mathematically possible if you have passive resistor values in your network like we've drawn here. But there are some weird transmission line or wave guiding phenomena that you can model with a negative alpha. Anyone ever heard of an erbium doped optical amplifier? This is actually what they use undersea communications nowadays. You know, everything's fiber optics going under the sea. And there's a section of line that they excite with a laser. They pump up these erbium doped atoms in an optical fiber. And so they're kind of stimulated, right? And as a optical pulse goes through them, it's just almost like an unconfined laser cavity. The excited erbium atoms give stimulated emission, will actually amplify the wave. So you get exponential increase of your signal as you go down that particular type of guided wave structure. You can model it with transmission line equations and use a negative alpha for that particular system. Very artificial way to make a negative alpha, but it sometimes happens that such systems can be modeled in that manner. And that's a nice thing because it turns out you can put those under the sea. And it doesn't matter which waveform, what type of protocol you want to use. You can basically just prime this thing up. Whatever waveform goes in comes out stronger on the other end. The old way of doing it was to put what's called a regenerative repeater at the bottom, which digitally demodulates, then reconstructs the signal, and then sends it out on the other end. But of course, that can become protocol specific. So it's easier, so much more elegant to just send it through a stimulated section of waveguide. Okay. Now, one thing I want to emphasize here now, this is a phasor solution. Let's just verify very quickly. If I have a forward propagating wave, no backwards propagating wave, that my complex phasor voltage that I've used to describe this solution, e to the minus propagation constant z, produces the type of behavior that I'm expecting. This is just a forward propagating wave. I don't have any backwards propagating wave. I'm going to expand this out so that it's exp to the minus j beta z, and then I also have a minus alpha z. When we come back, I will complete this calculation. We will convert this back into the time domain and just verify briefly that we get an exponentially decreasing sine wave. And then what I do is work a couple examples of how to calculate loss coefficients from spec sheets and figure out how much power you're actually going to lose on a transmission line. So I'll see you on Thursday. Great. Let's continue on with our discussion of lossy transmission lines. And you'll recall that one of the key results of the lossy transmission line was that if you had a voltage, a phasor voltage is a function of distance along the line. This would be equal to some amplitude and phase of an original forward propagating wave and we said that the one key difference in this solution, one of the key differences, is that our propagation constant is now not a pure imaginary J beta, but rather it has this attenuation coefficient. In addition to a wave number. And that manifests itself in exponentially decaying amplitudes in the positive z direction for a forward propagating wave. And of course, for the backwards propagating wave, it's the opposite. Decays in the negative z direction. Now, let's take the magnitude of this voltage, because in the end, it's the amplitude and the power, and not necessarily the phase, that does most of the work in our circuits. If we want to track the amount of energy in a signal, for example, which is extraordinarily important regarding its ability to carry information reliably, then we need to look at the amplitude of the voltage, or the amplitude of the voltage squared, which is relative to power. So let's take a look at this. We're going to take the amplitude of this entire thing, which is really the same as taking the amplitude of each individual component and multiplying them together. That means the amplitude of this thing, the amplitude of this attenuating exponential, times the amplitude of this complex exponential. Well, this guy, we can just write him as V plus without a squiggle. He'll have an amplitude, just getting rid of the phase when you take the amplitude of him. This is a positive real number, so I don't have to worry about taking the amplitude of a complex value. I can just write this as exp to the minus alpha z. It's always real and it's always positive. And what's the amplitude of any complex exponential? With a purely imaginary argument. 1. And we see that the amplitude has that exponential taper. Now, one of the things that we wanted to do, just to verify the behavior here, let's take this original expression and convert it back to the time domain, just so we have a feel of how to do that. A lot of times when you just work at problems in the phasor domain and again and again and again, you start to lose track of the fact that these things are, you can't measure a J on an oscilloscope. You can only measure a time-varying waveform. And what will that look like functionally in the time domain? So let's go ahead and reintroduce that. How do we convert a value back into the time domain? We take the real value of our phasor, which is a function of z, times the implicit sinusoidal frequency dependence, exp to the j, the plus j 2 pi ft, where f was the frequency of excitation. And if we do that, then we have the real value of, let's break this V. We got a V complex or phasor value amplitude and phase. And let's see, exp to the minus alpha. And I'm just going to lump these together. My alpha plus j beta, and that both multiplies z. Okay, this right here, we can make this a V plus amplitude. And of course, there's going to be some sort of phase j phi associated with that. I'm going to go ahead and take that phase and bring it into my exponential argument. Put it there, not there. Okay. Everything's good. So this is real, so I can take this out. I can factor this out. And actually, you know, that exponential minus alpha z part is real too. I can go ahead and factor that out. And what I'm left with is just the real value of exp to the minus j beta z plus j phi, which by Euler's law, we know breaks into cosine. Oh, and I forgot my plus j 2 pi f t. I got to put that in there too, right? Almost threw the baby out with the bathwater. Tragic. Okay, so I got a bunch of imaginary terms in my exponent. I know I can write that as the cosine of the sum of each of these things. 2 pi ft minus a beta z plus an arbitrary phase, and plus j sine the same thing. And I'm not even going to write it because we know we're going to get rid of this. We're taking just the real values. So the final answer in the time domain, the thing that you would measure with a scope at different points along the transmission line z, would have the following functional dependence. Volts. And you see we got that nice, beautiful traveling wave expression here. Frequency times time minus wave number times distance traveled, and an arbitrary phase value. Any point, if you set z equal to a constant, you get an oscillating sinusoid and exponential attenuation of the amplitude depending on how far along z is. It's a good exercise to work through, being able to convert a space-varying phasor back into a time-varying quantity, just to clarify the complexity. You know, this solution is a little bit more complex than those constant amplitude waves that go back and forth on the transmission line. So now I want to go back here, and we said that the magnitude of that voltage is equal to this. This is also called the envelope in units of volts. The envelope is the maximum displacement in voltage or current that you're looking at. And of course, I just told you earlier that in a lot of communications and applications, the real showstopper is power, right? So let's go over here and do a power calculation. Power in this waveform, well, power is equal to, in the sinusoidal world, 1/2 the real value. And if we're doing this as a function of z, we're going to take voltage as a function of z times current as a function of z, and I got to have a complex conjugate there. Don't forget that. A lot of you, where they came by office hours, I think because you guys don't have a lot of practice with sinusoidal circuits yet. You've only probably had one class with them, or at best you've seen them a little bit in the physics class. So it's really easy to forget this complex conjugate value, but you need that. Remember, complex conjugate, you just flip the sign on the imaginary part. And this gives you units of watts, presuming that you're using peak amplitude values. In this class, we always use peak amplitude values. It gets a little different when you go over to like the power engineering side of things, where a lot of times they'll be using RMS values, which means you don't have to put the 1/2 in front. Remember, this is really time averaged. If you take this off the front and use peak values, you're getting the instantaneous power when voltage and currents are at their peaks. There's also nulls along the way. And so when you average over time, when you do that with sinusoids, you always got to put a 1/2 there. And we can rewrite this a little bit more. Let's try this. 1/2 the real value of voltage. And we know if you got just a forward propagating wave here, I is really voltage over Z naught. I got to take the complex conjugate. So the way complex conjugate works, if I got a value over a value and I want to take complex conjugate of the whole thing, I just got to conjugate the numerator and the denominator. Well, what is any complex number times its complex conjugate?
Just the real part, just the real number?
No, not just the real number. It's actually the magnitude squared, right? It's actually one of the definitions. If you want to write the magnitude of a phasor, it's really the square root of that value times its complex conjugate. So this is actually magnitude of voltage squared, which of course is a real value. This means we can take it out there. So really what we got is 1/2 magnitude voltage squared times whatever the real part residual is of 1 over Z naught. Remember, when we're talking about lossy lines, Z naught can actually be a complex number, so we can't just pop this out like we could in the previous sections. So this is good, because we're about to derive one of the most important formulas. It's very simple, but it's one of the most important formulas in maybe electrical engineering as far as a practicing engineer goes, somebody who's reading spec sheets of cables and devices. So oh, do you have a question?
Oh, I was just going to point out that shouldn't be the, yeah.
Oh. Thanks. Okay. So, let's do a little experiment. What is P power evaluated at Z equals to 0? Well, I plug this in. For my lossy line, I get 1/2. Let's see, I said that the magnitude of this was V plus times that exponential attenuation factor. Here I'm squaring it, so I'm going to get V plus squared exp to the minus alpha z. But I got to square this. And of course, we square exponentials by just putting 2 in them, right? You just put 2 in the argument. That's like raising it to the second power. And let's see what else we have. We got to put that real value. 1 over Z naught complex conjugate. Now, what happens if we move 1 meter down the line? P of Z. Z is equal to 1 meter. And here, I need to substitute 0 into here. I'm going to use this as a template for my next expression, so I left it up here. But I need to put 0 in there. So what's that exp of 0 going to be? 1. 1. That's sort of my reference point. So the whole thing is really just 1. Now over here, I'm going to have this exact same expression, exp to the minus 2 alpha 1 for z, times the real value of 1 over z naught, complex conjugate, blah, 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 blah. Okay. So the ratio of these two values, the power that I started out with at z equals to 0, and the power that I experience when I go out to 1 meter, is actually a really nice metric for loss. It's basically the loss factor per unit per meter that I experience on the line. And so if I divide these equations out, you see a lot of nice things happen. I've got a 1 here. All this stuff cancels. I've got just an exp to the minus 2 alpha in the denominator, which becomes a plus 2 alpha in the argument of the exponential when I move it to the numerator. And this is basically the loss per meter. It's a unitless value. It tells you what fraction of your power are you going to lose going 1 meter along the line. And that loss is geometric, which means if you lose a factor of 6 going from z equals 0 to z equals 1, you're going to lose another factor of 6 going from z equals 1 to z equals 2. You're going to lose another factor of 6 going from z equals 2 to z equals 3. This is very elegant to track in the logarithmic domain. So for that reason, loss parameters, loss information about transmission lines is usually reported in dBs per meter. So let's figure out how to calculate that. We said our loss is equal to P evaluated at 0 and P evaluated at 1 meter. And that was exp to the plus 2 alpha z. To convert this ratio to the decibel scale, I need to take 10 log base 10, my power loss. Why 10 and not 20?
This is power, not voltage.
Yes, that's right. Power, not voltage. Very good. So I got to do 10 log base 10 to alpha. And this should be a 1 meter because we plugged that in already. And no, I forgot my exp. Okay. Well, remember, I always have a habit of writing exp as like a 3-letter transcendental function because it is intimately related to sines and cosines, right? And hyperbolic sines and cosines and all those fun transcendental functions. But of course, we all know that this is really the same as 2.718 blah, 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 raised to the 2 alpha power. And if I take the log of something raised to the power, I can rewrite that as just 10 with that exponent brought out in front of the logarithm. Does everybody remember? Does everybody remember that formula? Dust off your high school algebra or maybe your early calc discussions. When you take the log of something raised to a power, you can take that that power out in front of the logarithm and just take the log of the base. Yeah, it's in there somewhere, right? Everybody's kind of like, oh yeah, I remember that math. It's not something you use every day. So log 10 of E, really what we have is 20 times alpha times log 10 of E. And if you plug this in the calculator and group it with the 20, you get 8.7 alpha. And this has units of dBs per meter. This is the kind of spec that you would typically read off of a cable. It would give you dBs per meter. And then you could calculate how much loss you're going to incur if I have 100 meters of cable length. If it's 0.1 dBs per meter, then all you have to do is multiply by the length, and you realize you're going to lose 10 dB total when you put the signal in from this end to the other end. 10 dB, that's just a factor of 10. I'm going to have 1/10 the power at the end of that cable. See how easy it is? dB scale is a wonderful scale to work with. You probably don't have a lot of intuition in working with the dB scale yet, but it's great because a lot of the quantities that we deal with in electrical engineering have such disparate orders of magnitude. For example, in wireless communications, we use dBs all the time because what we transmit with, I mean, there's some devices that transmit with kilowatts or megawatts. And we've got kilowatts over at WREK pumping into the antenna. So you need a big number to transmit, to record the transmitted power there. But when you go to what the signal strength is at the terminals of an antenna, you're talking femtowatts. We just spanned, 18 orders of magnitude going from point A to point B. This is why the dB scale is so useful. There's another reason, because losses in cables tend to accumulate geometrically. dB scale is great for geometrical loss accumulation. So it probably won't happen now, but if you take 3065 and maybe some antenna engineering and you kind of go that route, by the end of your undergraduate days, you'll be able to think in dB. My problem is that everything I think of in dB, I go to the grocery store and I'm like, oh look, that cantaloupe is 75% off. Oh, it's 6 dB off. I was bucking for a 1 dB pay raise from my boss the other day. He thought I was crazy. No, I'm just kidding. We haven't gotten raises in years. So, yeah, this is a very useful number to have. What are the units of this? I think I said last time, these are Neppers per meter. Sometimes often called the Napier, because it's really named after John Napier, the inventor of the logarithms. So we call them Neppers per meter. It's really unitless in a way. But this is how to convert between Neppers per meter and dBs per meter, multiplied by 8.7. As a side note, this is logarithmic attenuation. I think the problem on the next homework, which I won't assign until next week, will involve some tracking of power levels in some lossy cables. And I may use logarithmic power, not just logarithmic loss, but logarithmic power. What do I mean by that? Well, when you're dealing in the dB scale, quite often you want to express your powers in dBs too. So for example, if you have a value in watts, if you take 10 log base 10, this is the unit dBW, decibel watts. It's a common form of expression of power in the logarithmic domain that RF engineers use, especially when you're talking about transmitters. So for example, if I was WREK and I was transmitting 10,000 watts, that's 40 dBW when I take 10 log base 10 of that. When you're talking more about like mobile receivers and mobile transmitters, those are less power. Hopefully your cell phone isn't putting out 10,000 watts. The battery wouldn't last very long, and you'd probably feel it in a matter of milliseconds if it was. In that case, for those smaller values, especially at receivers, we like to do 10 log base 10, the value in milliwatts. And that we give a special unit, dB little m, dBms. So 30 dBm is 1,000 milliwatts, which is the same as a watt. In fact, if you ever want to convert from dBWs to dBms, you just add 30 to dBW. It's really amazing, though, because if you think about it, like a cellular phone can operate with signals. It can decode signals with receive powers less than negative 100 dBm. That's 10 to the negative 10 milliwatts. That's why we have to go all the way down there and use that logarithmic scale to talk about those tiny little levels. Yeah, do you have a question?
Yeah. What did you say about the 30?
What did I say about the 30? Oh, when you're converting from dBWs to dBms, you just add 30. Because it's 3 orders of magnitude in the decibel scale larger, 1,000 times larger in the linear scale. How many people have seen the unit dBm before? Yeah, I hope you have. And you have too. Good. You have? Where did you see it? In what? Oh, another teacher taught you, huh?
Yeah.
Sweet. You've used it before. That's good news. Anyway, once you get something in dBm, it's nice because then you can start adding this quantity, 8.7 times alpha, or the loss in units of dBs per meter. You can track power very easily in that case. So any questions? Any questions so far? No? Well, we gave you the general solution for lossy transmission lines. What I'm going to do now is put on some analytics on the board that allow you to deal with a special case called the low-loss transmission line. And really, I would say 99% of the time, that's the transmission line that you're going to be practically dealing with as engineers. Because if it becomes a high-loss transmission line, if it violates our low-loss assumptions, it is probably a pretty crummy transmission line, and you shouldn't be doing it. You shouldn't be using it, right? So for most analysis, the equations that I put on the board here are useful simplifications that will allow you to deal with these problems. Just recognize that there is this implicit assumption that you're not losing a significant amount of power over a wavelength of distance along the transmission line. If that happens, all bets are off, and you got to go back to what we did in the first part of this lecture earlier. So let's do the low-loss approximation for transmission lines. Okay, for the low-loss lines, or lossy lines in general, we had this propagation constant, which we said was the square root of my per unit length series resistance, the ohmic losses on my transmission line, plus J2 pi f, the per unit length inductance on the transmission line, times the per unit length shunt losses, or shunt conductance, G, added to J2 pi f, my per unit length capacitance. And that was the full-on expression, no approximations necessary. And so what I'm going to do here, I am going to factor out a J2 pi f square root of LC, which leaves under the square root 1 plus r J2 pi FL times 1 plus G J2 pi F C. Just factoring out. And when you have 1 plus a little bit of something times 1 plus a little bit of something under the square root, you can actually write this as approximately, for r much less than 2 pi fl, and g much less than 2 pi fc, which is our formal criterion for low loss. You can write this as 2 pi f square root of LC, the quantity 1 plus rj 2 pi fl times 1 plus g j 2 pi fc. So all we did was really get rid of that square root, because you can actually do that when the arguments are really small. And for further approximation, now it becomes just a multiply the ones, multiply these two things, which is going to give you a very small number, because you got small thing times small thing. We're going to neglect that. And then we're just going to worry about the cross terms with the complex numbers. And when we do that, we get j 2 pi f square root of LC 1 plus 1 over j 2 pi f r over L plus g over c. And the reason why we write it in this manner is that by doing so, we now have a nice expression that has broken itself neatly already into real and imaginary parts. We know that the real part, which is going to happen when you multiply this by this part, gives us an expression for attenuation factor, alpha. And j 2 pi f square root of LC times this 1 gives you the complex wave number, j beta. In fact, it's the same beta that we had in the lossless case. And so that's actually one of the key approximations in all this. It says that, you've got to calculate the propagation constant in all its full glory if you want the exact solution. But if it's a low loss line, then you can basically just say that beta is 2 pi f square root of LC, just like you could in the lossless line. It's not going to differ that much. In fact, we can also say that about the impedance. And so my final low loss formulas are going to be given by the following expressions. Beta is going to be approximately equal to 2 pi f the square root of LC in radians per meter, like the lossless case. My z naught, if I go ahead and calculate that with very low values, this is going to be equal to the square root of L over C, ohms. My intrinsic impedance is, again, just like the lossless line case. The only thing different is that we've got an alpha, and that alpha is approximately equal to R over 2 square root of C over L plus G over 2, my shunt conductance, square root of L over C. And of course, this is in Neppers per meter. So this is comforting, because what it really means is that everything we've learned about transmission lines is valid for the lossy line, as long as the loss isn't too much. We can use all of our same formulas. The only thing we have to do is calculate a quick attenuation value and slap that exp to the minus alpha in front of our forward traveling wave, and an exp to the plus alpha z for a backwards traveling wave. Everything else is the same. Intrinsic impedance is approximately real.
Is that a 2 or a Z?
These are 2s. Z's I always put on them. Now, when I will give you a homework assignment, and that tests this out next week. And for one of the problems, I will make it in such a way that you will have to use the full loss formulas just to see the difference. So I'll clue you in on that when that happens. Just so that you can, it's one of those things like convolution. You work through it once in your lifetime, and then you realize you never want to do it again, right?
Can you put a note that says use whole formula?
I will. If you ever get in a situation where you can't use the low loss approximations, the nice thing about this is that you're going to basically use your impedance transformation formulas over short distances. Over long distances where you accumulate a lot of loss, or under short distances where it's a really lossy line, you have to punt and use this general impedance transformation formula. And remember, this is where I've got a transmission line. It's terminated by some sort of Z sub L impedance. It is being operated at a wave number of beta, an intrinsic impedance of Z naught, and it has a distance D. And the question is, what is the input impedance here, my Thevenin equivalent? The formula for this is Zn is equal to Z naught times my load plus Z naught hyperbolic tangent tan h beta d, actually propagation constant d, Z naught plus ZL tan h propagation constant d. Now, what is tan h, or hyperbolic tangent? Well, remember that regular tangent is equal to, if you take the tangent of x, what you're really doing is take an exp jx minus exp to the minus jx over j exp to the jx plus exp to the minus jx. If you want to use complex exponentials, that's how you define the regular tangent. It's really just Euler's law for the sine divided by Euler's law for the cosine, right? Everybody sees that? Well, guess what hyperbolic tangent is? It's the same thing, except you just take the j's away. So when you have a complex propagation constant, you got to use this full-on expression. You can probably see through inspection that when you make a purely imaginary propagation constant, all of a sudden I've got j's all over the place, and it defaults to my original tangent expression. If you use this identity, tangent hyperbolic of jx is equal to j tangent x. If you do that, then what you find is that you recover those original expressions when you have a complex x's. The original impedance transformation for the lossless line. So just put that in your notes. We're probably not going to do anything with that quite that involved. But recognize if you ever do come across a situation where you need to load transform a load on a complex line, that's the general formula to do it. Yeah, Cameron.
So that's what happened to the like the normal J. That would be like Z0 J tan of beta D, and the other formula is the hyperbolic tangent. Just
yeah, that's right.
brings the J in, so.
When gamma, your propagation constant, was purely imaginary, in other words, there was no attenuation coefficient, gamma is equal to J beta. If you plug that in and work through those trigonometric identities, you can show that your formula that you learned for the lossless case was really just a special case of that formula. The really ugly, full-on hyperbolic tangent formula. Okay, let's cover a couple things that are more practical now. I want to talk about this result a little bit more. One of the nice things that we like about the low loss formula is that it conveniently breaks down loss into two components. Notice I got something here that involves series resistance and something here that involves shunt conductance. As a result, a lot of times you'll see books and spec sheets break this into alpha sub C and alpha sub D, because they neatly correspond to two different physical mechanisms. Alpha sub C are your conductor losses. Your nepers per meter due to the fact that you have series resistance in your transmission line. These are often your dielectric losses. The dielectric loss, or perhaps stray conductivity that you have in your dielectric medium, causing loss in waves that propagate down your coaxial cable or twisted pair or whatever. In fact, we can rewrite these as R alpha sub C. My conductor losses is R over 2 Z naught. And my dielectric losses are G times Z naught over 2. We got ohms over ohms, Siemens times ohms, both of which are unitless. This one is typically more important for long cable runs at UHF frequencies and lower. It's usually the conductor losses that are building up. When you get into microwave frequencies, you can have a significant amount of dielectric loss as well, but this is usually the culprit in everyday life in terms of what's contributing to the loss in your cable. Now, the thing about this guy, though, is that he is frequency dependent. Alpha sub C is frequency dependent. And you think, well, it's basically a function of the series resistance, and usually the conductivity of a metal doesn't change appreciably over octaves of frequency. However, there is another effect, which you may have seen a little bit in physics, called the skin effect. When you were studying metal in physics, here's your metal or conductor. You learned that currents, they just kind of set themselves up uniformly over the cross section. So that if you looked at this cross section here, you would get nice current vectors evenly distributed, coulombs per second per meter, describing current flowing nicely through the conductor. It would be a constant value in amps per meter squared that you use to describe the flow through there. But when you start to introduce frequency, and you actually go through and solve Maxwell's equations, what you can show is that the current flowing in that same direction jumps out to the outside of the conductor. In fact, the higher the frequency, if you blow this up, here's my blow up of the surface. Let's take that area there and blow it up. The conductor with the current on it has a distribution such that if you measure it as you go into the conductive medium, there's an exp to the minus, let's call it x over delta, where delta is the skin depth, measured in SI units of meters. Thus, even though it technically doesn't go to zero if you go to the center of the wire, most of the current is carried within the first couple skin depths. In fact, one way to think of the skin depth is that if I went one skin depth into the material, and I took that skin depth and multiplied it by the perimeter, this is what I actually have as an equivalent cross-sectional area for carrying current, A. So you remember in your old resistive formulas, you'd say that a resistance of an object is equal to its proportional to its length. Longer the thing is, the more resistance you have to go through it, divided by the conductivity. The bigger the conductivity, the less resistance it offers. Also divided by the cross-sectional area. Because the analogy is that the resistance is kind of like a pipe. The bigger the cross-section of your pipe, the more flow it allows without obstruction. So you have this nice formula, resistance is equal to L over sigma A. And as long as you were operating in DC, that's fine. You can use the cross-sectional, the physical area, A, as your cross-sectional area. Well, as soon as you have AC, you can use that same formula, but you have to take into account that the cross-sectional area, equivalently, is really only on the surface of any conductor. Which means that my A here, one way to estimate that is to multiply the skin depth times the perimeter. In this case, it would be 2 pi r, the circumference of this circular section that I drew on the board, times a little skin depth. Now, the important thing to recognize, too, is that we have a very simple formula for skin depth. Delta is equal to the 1 over the square root of pi, frequency, conductivity, permeability of the metal. This is conductivity. This is magnetic permeability. Usually mu naught, unless you're dealing with steel or something like that. And of course, this is just frequency. Siemens per meter, Henrys per meter, hertz. And if you do all that together, that's basically units of meters. Take 1 over the square root. So you see what happens. Well, usually this is mu naught, so that doesn't affect that much. Conductivity, interestingly enough, the higher the conductivity is, the more the current spreads out to the outside. The higher the conductivity, the more it spreads out to the outside. That's actually bad, right? So the question is it better to have high conductivity or low conductivity at AC if you want to minimize your resistance? Low conductivity. Well, if the skin depth was the only thing at work, that would be true. But remember, your series resistance, or your per unit length resistance, is going to be 1 over sigma times A. So your equivalent cross-sectional area is going to drop 1 over the square root of sigma. But you got a whole sigma in the denominator. So there is a net 1 over square root of sigma still. So higher conductivity is always better than lower conductivity if you're trying to minimize resistance. Just recognize that there's not a perfectly linear trend when you're talking about AC signals. The other thing to recognize is that there's a 1 over square root of F dependence in the skin depth. The higher the frequency, the closer things cling to the outside. We can see this in power engineering, this effect most readily if you just go outside and look at a high voltage line. And you'll see the different phases that they're carrying on the high voltage line, and they're high tension wires. And what they could do is carry in one big giant cable all of the current. But it's 60 hertz AC, it's alternating current. And the skin depth for a typical conductor, Xingjin, do you know what the skin depth is for a typical conductor? I forget. About 9 millimeters, almost a centimeter, right? Yeah, so you'd only get about a centimeter's worth of conductivity around the outside. The rest of this is wasted metal, right? And so you don't ever see really big wires that try to minimize minimize resistance by making as much conductor as possible. Instead, what you'll see is 1, 2, or 3, or sometimes 4 wires with a little spacer in between them carrying the current. These wires are actually all at the same potential. They're all part of one phase on the transmission line. But they're taking advantage of the fact that you use less volume of material and you can get more perimeter space on your tiny cables, on a bundle of tiny cables, than you can on one big cable. And thus, over the miles and miles of runs of cable, you save millions and millions of dollars as an engineer. So depending on how long and how high the voltage is and how much loss there is, you'll see sometimes 2, you'll see sometimes 3, and then you'll see sometimes 4 on the really high-powered lines. Anybody ever notice that walking around? Okay, so let's use this in an example. For a coaxial line, one of our most favorite forms of transmission line, my conductor losses, alpha sub c, is equal to the square root of F, there's that square root of frequency dependence, divided by 4 Z naught. Z naught is in the denominator. Higher impedance means less loss, less conductor loss. Square root of mu over pi sigma, higher conductivity, less loss. 1 over A plus 1 over B, where recall on my coaxial cable, A is the inner conductor, radius, and B is the outer conductor. Radius. Which one of these terms is going to dominate the expression? almost exclusively A, right? A is a small number, so when you take 1 over A, it should be a lot bigger than 1 over B. You can put this term in for completeness, but really this is going to be where the rubber hits the road, so to speak, in your calculation. Let's see. Oh, yeah, we have plenty of time to do it. A short example using this expression. Let's do a sample calculation. Get some numbers to all these formulas so that we know what we're physically dealing with. And our example is going to involve a cable modem. Providing internet to your home. So how does this work? Okay, you got a cable. And if you looked at the cable on a spectrum analyzer, it goes from, say, DC to about 1 gigahertz, 1,000 megahertz. Your cable channels, in the old analog systems at least, and then they kind of munged them in the digital formats later, all used to occupy about 65 megahertz all the way up to about 850 megahertz. And in the old schemes for the analog channels, used to have these little 6 megahertz vestigial sideband modulated signals populating through here. And there's a variety of digital formats that you can use. But the point is, there was a little bit up here and a little bit of spectrum down here that you could use for the uplink and the downlink of your internet service. So here we've got about 150 megahertz of spectrum. And down here we've got as low as 5 megahertz of spectrum. So this is about 60 megahertz that was used. This part is the uplink, which means you're sending data packets in this signal spectrum modulated on a carrier from your home to the next data point in your cable network. So you're sending it to your ISP. These are for the packets that are raining down from your ISP down to your computer. And they're called uplink and downlink, respectively. So obviously, people tend to consume a lot more data than they produce, which is why you get the big band up here to the downlink, and the little band down here to the uplink, right? Now, let's ask the question. Let's use what we know to figure out what's the difference in attenuation between the highest frequency in the downlink compared to the lowest frequency in the uplink. You know, there's just some more spectrum available up here, so that's one of the reasons why we put the downlink up here. What might another reason be for putting the downlink at the higher frequency instead of the lower? Well, we just said that, and that's the same thing.
Bandwidth.
That's the same thing. Good, good. I like this informational equivalence that you're all understanding. Okay, what is our lecture today on?
Less loss.
Loss. Yeah, there's less loss down here. Why do you want less loss down here? Well, generally speaking, yeah, the little set-top devices on top of your television or behind your computer, that's basically your cable modem. You don't want to put expensive high-powered amplifiers in them because it makes the device cost more. It sucks a lot of power. Probably risk more home fires. You want to be able to have a low-power device send signals and still make it down a couple hundred meters of cable length to get to the next regenerative repeater, the next amplifier in your network. You have the luxury of making a nice cabinet that heats up with some, HVAC control or some, thermal controls on it that has a high-powered amplifier up here that sends a signal to your house. So you'd rather put the burden of power on the infrastructure rather than the consumer devices. And that is a trade-off that you will see again and again and again and again in all of commercial engineering. Push the complexity to the infrastructure, not the user. Okay, so what is the coaxial? Let's talk about the specs that the coaxial line that carries these signals will have. My coaxial line, we will treat this as if it had an interconductor radius of 0.5 millimeters and an outer conductor radius of 5 millimeters. This is about a centimeter diameter cable. We're going to say that this is standard TV coax, so its Z naught equals to 75 ohms. Not so lossy, so it's going to be purely real, but we will calculate that slight attenuation coefficient. And we're going to say that the skin effects and the conductive losses dominate. Copper, by the way, which is what we like to make that interconductor from, if it's made from copper, sigma is equal to 5.96 times 10 to the 7th Siemens per meter. 1 over ohms times 1 over meters. And the permeability is free space. 4 pi times 10 to the negative 7th henries per meter. So let's go ahead and plug these numbers in. Alpha, as a function of frequency, we say is approximately equal to alpha sub c, which will be equal to the square root of f that we have over there on that board, times 4 times 75 ohms in my denominator, times the square root of mu over sigma pi. This all evaluates to 8.19 times 10 to the negative 8. If I plug it all into the calculator. And my geometrical factor is 1 over 0.0005 meters. That's my A. Remember, A was 0.5 millimeters, my interconductor radius. So that's 0.0005 meters in SI units. And plus 1 over 0.005 meters for my half a centimeter outer conductor. And when all is said and done, I get this handy dandy little formula, 6 times 10 to the negative 7th square root of f, and that's nepers per meter. A nice rule of thumb for a simple television cable. Alpha, evaluated at 5 megahertz, is equal to 1.3 times 10 to the negative 3rd nepers per meter. But wait, we want to be good engineers. We want to be practical. Let's put this in dBs per meter. Multiply by 8.7. 0.012 dBs per meter. Not very lossy, actually. If I'm at 5 megahertz on one of these standard coax lines, if I go 100 meters, how much loss have I incurred? 1.2 dB. That's not even half. That's only a small fraction of your power that is lost. That's the good news. Let's look at alpha as a function of 1 gigahertz, the upper end of the spectrum. I plug it into the magic professor calculator, and all of a sudden I get 0.019 nepers per meter. or multiply by 8.7, 0.165 dBs per meter. That's quite a bit more loss. So remember, that's in the dB scale. If I have 100 meters of cable length, I will have lost 16.5 dBs of signal strength. What is that in the linear scale? Yeah, that's a factor of 40. I now have 1/40th of the power that I originally started with. And so this is why you want to put the lossy frequencies, let the infrastructure amplifiers transmit those, and keep the set-top boxes transmitting the weak stuff. Yeah, Blanca.
Shouldn't the losses be negative?
Because if it's dB and it's positive, it means that's higher than 100%.
Yeah, so the convention is if you call something a gain, if we call this a gain, then it would be negative.
Okay.
If we call it a loss, then it's a positive value. So it's, yes, sort of which side of the fence you're looking on. Whenever we talk about loss, we always we negate the amount of attenuation. Any other questions? Well, that's it. We are now officially done. Lossy Lines. Good luck.